So what do you guys think about chapter 5? Do you feel like it's a little better than chapter 4 or same? Okay, it's good. Okay. Yeah. I know this is totally biased because you guys come here every day. So it's a little bit easier for you guys. You come here every day. And normally people who show up in lectures are people who put most time on the class. So but okay, yeah, good. Another thing is your brain kind of get used to it after a while of all these flooding of math and physics into your head. You know, you were not used to that before, but now you're used to it. So if you keep going on, you'll be a physicist. You know, just take more and more physics classes. Your brain gonna get used to it more and more, and then one day your brain will feel like, I love the stuff. You know, I need to do it all the time. You know, something like that. Okay. Okay, so what we did yesterday was we talked about after the 3 topics, right? In this chapter, we start from work, and you guys can see the whiteboard, right? Okay. We start from work, like defined like this, and we went to kinetic energy after that, and we developed work kinetic energy theorem. And then we talked about potential energy, which is related to, so mostly we talk about gravitational potential energy, which is related to work done by conservative force, in this case, gravity. And then we talked about, so we have this relation because work done by gravity is independent of the path, we can calculate this work by using this negative delta P, Pi minus Pf, okay? And then we talked about energy conservation, which is putting everything together. So in general, the total mechanical energy, which is defined as kinetic plus potential, the change of that energy equals to work done by non-conservative force. That means if there's no work done by non-conservative force, there's no change in the total energy. That's called energy conservation. We can write EI equal to EF. And then basically saying no free lunch. You have to, if you want to get some energy, you have to get some from some other kind of energy. You cannot simply create energy from nowhere. Okay, and then we got we talked about a couple of applications to show you how to calculate use energy conservation. The critical thing here for each problem is to choose 2 states. Normally we call them initial states and final states. Okay, choose these 2 states to focus on, you know, and then write down their energies. Okay, some of them are these terms are 0. Okay, and then from there you got your answer. Okay, now we did an exercise together about this. Yeah, so yesterday we had some extra credit because you guys did the exercise. So and we talk about, I mean, this is pretty straightforward, right? So today, let me just talk a little more, like 2 more subjects, which are all pretty tiny, but I now remember, I looked at my notes from last time I teach this class, so I realized there's a couple more topics. So basically two topics I want to talk about. Okay, first, so this is going to be called number 5, I think. Okay, let's talk a little bit about power. Okay, I'm not going to go to whole depths of it, but I think it's a very useful concept to know, and it's actually coming from every life. You see it every day. I mean, in your life. So what is power? Power is, roughly speaking, you can define power. We use P for that. Okay, P equals to, roughly speaking, the work divided by the time. Okay. So normally we measure power to a machine, or like it could be human as well. So what we count is like consider a given time interval and then measure how much work can be done by this machine. Take the work divided by the time interval. That gives us power. Okay. Well, because the unit for work is joule, unit for time is second, so the unit for power is joule per second, okay? And we have a new name for it called watt. excuse me. That basically is again come from name of a person. He actually developed a. He's not the first guy, but he actually made a really good steam engine that worked really well. So he's an engineer, I think. So they use his name to name the power. So well, when you look at your when you look at your electronic devices at home, you see this unit a lot, right? For example, a light bulb. On the light bulb, normally they tell you the power of it, and it's like a 100 W, 100 watt, okay? Or it could be 40 watt or 60 watt. These are basically it's telling you the power here. So it meaning like every second is gonna consume 100 joule energy, okay? So that's how much energy is consumed, okay? Well, your laptop, your TV, your cell phone, they all consume energy, and then all the power, you can check their power, and then you can add them up. They kind of give you an estimate about how much energy you need to use per second. Well, on your electricity bill, you see not power, but something like this, you see kWh, okay? So what is that? It's kilowatt times hour, okay? So kilowatt and times hour, okay? That's your electricity bill, okay? So this is not a unit for power because this part here is unit for power. So if you take the power times the time, it actually, this is a unit for energy, okay? Kilowatt hour is a unit for energy, okay? But notice it's a much bigger unit than joule because kilowatt hour, so 1 kWh equals basically 1,000 watt times 3,600 second, right? Because this is how much 1 hour you have, right? So together, this gives you 3.6 times 10 to the 6 watt times second, which is joule. So 1 kilowatt hour is 3 times 6, 10 to 6 joule, okay? So it's a way bigger unit of energy than joule, but it's a very convenient unit to have for your electricity bill. For example, if you keep your light bulb, let's say you keep your light bulb on at night, you forgot to turn it off for the whole night, okay? The whole night, okay? Let's say you sleep like 8 hour, right? Let's say this is 8 hour. And let's say your light bulb is a 100-watt light bulb, although a lot of light bulb right now, they're like LED light bulbs, saving energy. So it could be like only 40, but let's, for the example of, for the purpose of giving example, let's consider this too. So that means the energy you use for this, you take them together, it's gonna be 100 watt times 8 hour. Well, you can put this as 0.1 kilowatt times 8 hours. So that's gonna be like 0.8 kilowatt hour, okay? So if you keep your light bulb, 100-watt light bulb on for the whole night, about 8 hours, you're gonna get the energy is used is 0.8 kilowatt hour. So normally they charge you electricity in terms of kilowatt hour. So 1 kilowatt hour, normally they give you like a fixed amount, like I don't really know, maybe 40 cents or something. Well, depending on how much you use, the more you use, you get like a more like discount or something. But this is directly related to the electricity bill, okay? Now you can estimate how much it costs for you in terms of the money, like this, like what we're doing here, okay? So this could save you some money, actual money by, knowing this unit. Okay, another thing about power I want to mention is called, there's another unit called horsepower, okay? Or HP for short, okay? Well, this unit is used mostly for engines, okay? So when you buy a car, normally it will tell you how much, so like car engine, okay? How many horsepower does this car provide, okay? Okay, for a typical sedan, it could go all the way from like 100 horsepower to like 200 horsepower, okay? Well, this unit, as you can tell, originate from measuring the unit of the power a horse can produce, okay? And you can tell like in modern time, the cars are pretty powerful, right? It's roughly speaking about 100 horses. It's like a equivalent to have you 100 horses pulling the car all together, right? Think about that, right? It's way powerful than the horse, that single horse wagon or something, you know? So, and the 1 horsepower is about 700 watt. Okay. Well, I don't remember the exact number. Let me look it up. So make sure I got it right. 1 horsepower, 1 power to watt, 2 watts. Okay. Okay, 745.7 watt. Okay. So it's pretty big. So your engine is really powerful. Okay, so you have 100 horsepower, right? That's like a lot of watts. So that's why you can easily use when you drive your car, right? You can use your car to charge your cell phone. You know, when if you have some USB plug or something, it wouldn't matter much for the car because it's really powerful. It can produce tons of power every single second. Okay, so I think this is all I wanted you guys know about power. There might be one homework problem about power that you can use this kind of, it's a pretty simple idea, you know. Okay, so the last one here, I realized that I might put one problem on this in homework. So we'll talk about this a little bit as well, which is another kind of potential energy, which we call like a elastic potential energy or spring potential energy. Or spring potential energy. Okay. So again, our focus would be on gravitational potential energy. So we only need to know a little bit of elastic potential energy. So what this says is if you have a piece of spring, you know, the spring can be either stretched or released or compressed. Okay. Well, if you say that if this is the relaxed length of the spring, when it's stretched, it's getting a little longer, and then we'll call this additional distance to be x. Okay. Well, when if you compress it, it's also going to be x. Okay. So basically, the deformation, x is the amount of deformation from the relaxed state. Okay, so that's the deformation here. So 5, 6, 7, 8. Yes. So we actually we can define the force given by the spring as the spring force equal to negative kx, where this k here is the so-called spring constant. Okay. And then correspondingly, we will have a spring potential energy we call PES equals 1/2 kx squared. Okay, so and you can easily show that this force is a conservative force because basically there's no other path you can go from one position to another position here. It's all one dimensional. So in this sense, it has to be conservative because the work is independent of the path because there's only one path basically. So anyway, so that's your spring potential energy. So let me give you an example of spring energy, potential energy. Again, it is not the emphasis of us, but I think it's kind of useful. And then for some of the problems, for some of you who take like a MCAT or something, you may need to know a little bit of that. So let me go to chapter 5. Oh, wow, this is too much. So maybe a little bit less. Okay. So, okay, this is the energy. So let me just give you one example about spring energy, solving problem with spring potential energy. Okay. So that's gonna be like, where is it? Hold on. Let me, okay, this is about power. We just talked about that. And then, okay, this one, circus acrobat. Okay. So, okay, see this one is actually jumping on a springboard. Okay. Now, so basically it says a 50 kilogram circuit acrobat drops from a height of 2 meters straight down onto a springboard with a force constant of this. Okay, this is our spring constant, or it's called force constant sometimes. Now I ask, by what maximum distance does she compress the spring? Okay, so let me go back to, this is our example 5.10. Wait, where is my, okay, here we go. So the information we know here is the mass of the person. Okay, I think that's 50, right? 50, 50, and then 2, and then 8,000 basically. Okay, 50 kilogram, and then starting from height of 2 meter, and then the spring constant is given as 8,000 Newton per meter. Okay, so this is basically the unit here come from here, Newton divided by meter. So it's that. Okay, so let's draw this picture together. Okay, there's this person. Okay, and then starting from this height here. So this is the springboard. This is the H here. Okay. Now you're looking for, I mean, after the person falls to the board, right? We understand that the springs are going to be compressed for sure. So it's going to go with certain distance. Okay, when after the person is here. Okay. Well, this one, let's just call it X, or I mean, or D as in the book. Okay. Or we can call it X. Let's call it X then. Well, it asks you about what is X. Okay. Well, this kind of problem seems like crazy, right? If you don't know energy stuff, right? If you want to use force to do all these study and everything, you don't really know what to do. I mean, or some things pretty complicated. But with the energy point of view, I mean, it'd be easier. So again, we need to make sure we can use energy conservation first. Okay. So when the person is in the air, there's only gravity doing work, which is a conservative force. When it touches the board here, it's basically given the force applied to the person essentially is coming from the spring. So that's the spring force. That's another conservative force. So so the energy of the whole system for the person is conserved. Okay. So how do we solve the problem? Okay. It's very simple. We choose two states to look at, and then we compare. I mean, we set the energy equal to each other. So well, this is obviously like one choice initial state. Well, this would be like the final state. Okay. Let's again write EI equals to EF. Now for this problem, okay, let's consider what kind of energy do we have, okay, for this person. Well, at the initial state, right, the person, oh, okay, I think it should be saying that the person is starting from the rest. Okay, it says drops from a height. So it should be at rest. Okay, so it didn't say it clearly, but it's actually at rest. Okay, so if it's at rest, there's no kinetic energy, right? So, but there's a given height here, so there's going to be gravitational potential energy at the very beginning. So, let's put this as a PE. I'll put a G here, PEG. Okay, all right, and that's all we have here, right? So what kind of energy does the person have in the final state when it reaches here? Again, when it reaches the lowest position, the person stops, right? So there's no kinetic energy again. So there's going to be gravitational potential energy at the final states, but there's also going to be this spring potential energy. I'll put it like PES, okay, at the final state, because the spring is going to be compressed. So in this problem, as you see here, although the person is moving, because at the initial and final state, there's no speed, so the there's no kinetic energy involved in this energy conservation. So if we write them explicitly, we'll write like this one be mgh, right? So actually here we take this as our zero reference plane, h equals 0. So mgh is the initial planetary energy, and then now when it goes to the final planetary, I mean it's going a little bit below that. So you can write the mgx, but let's put a minus sign explicitly. So it's going to be negative planetary energy, gravitational planetary when it reaches the lowest state, because it's going to be lower than h equals 0 height. Okay. We also have this spring planetary energy, which is given 1/2 kx squared. This comes from this planetary energy we just talked about. Okay. So we have these two energies, and they have to equal each other because the total energy is conserved. And we're interested in the x here, right? This is going to be our unknown. Okay. Now, I guess the next step is just to solve this. Okay. So we have one unknown. We have everything else, m and h and k, we all know. But the only issue here is you got a quadratic equation. I guess I didn't choose a good example, because I told you guys, normally you don't need to worry about the quadratic equation. So here we do have a quadratic equation with x squared and x term here, which is not you guys mostly need to do. But anyway, just for the demonstration purpose, let me go ahead and solve this, and then we'll, so that we know what's going on. So basically, you can plug in numbers right here, which make it a little bit easier for you guys to see. So 8,000 divided by 2, that's 4,000. So you have 4,000 x squared here. Well, this term here minus mgx, m is 50, g is 9.8. So that gives you 98 times 5, right? So 490x, okay, that's this term. Now this term, you want to move it to the right, so it becomes negative as well. So you have negative 490 times height h, which is 2. So you got 980, okay? So that's your quadratic equation here. From there, you can solve for the x by using quadratic formula. Again, you don't need it. I don't think we're going to have a quadratic equation in the test or in the homework. So I'm just using this example to show this specific case. So using the quadratic formula, you have 2 times 4,000. And then on the numerator, you have 490 plus minus square root of 490 squared minus 4 times 4,000 times 980 minus 90. So it becomes plus 90. Okay. So this follows from quadratic equation. If you have ax squared plus bx plus c equals 0, x equals to 2a, and then negative b plus minus b squared minus 4ac. Okay. Anyway, so plug all of these together, you get your x. Now there's 2 terms here, but one of them is going to be negative. So which is we assume x to be positive. So that rule we don't need. We only need the one root that has this plus sign here. So I guess I'll just ignore all these calculations because that's not very important for this purpose. So I'll just, I'll just leave it like, put it this. You got basically 0.56, okay, 0.56 meter as your result. Okay, I guess, again, the goal of this example is to just show you how to consider another potential energy in the system. When you have a spring presented, you have a different kind of potential energy, and then use the energy conservation. You can set up them like this, and then you can solve for x. Okay, but again, it's not my point to, it's not my goal to let you guys do the quadratic equation. It just happened that this one has quadratic equation. Okay, so okay, that's all we need to talk about for this chapter. Okay. As I said, maybe let's do an exercise because you guys are here. I want to give you some bonus points. So let's do the final exercise, okay? We're gonna do like one really realistic one for you. Let's say you have, okay, let's do one about power, okay? So I would just write something come up from my mind. So say you live in an apartment, right? Let's say you have a couple of devices there, like a refrigerator. Okay, we have a 200-volt refrigerator, and we have a 100-watt light bulb. And then we have a 50-inch LED TV. That's only 85 watt. Okay, so I guess the bottom line here, you can see here, right? A lot of your devices here are really not very using a whole lot of power. And the light bulb amazingly use tons of power if you use the traditional one. So let's consider these three devices, okay? Let's say, suppose you run this one as, I mean, this I guess is a full day, right? So 24 hours, this is one day. And for this one, you use like 8 hours at night. I mean, 8 hours too much. Yeah, 8 hours. Let's say 8 hours. The TV, let's say 4 hours. Okay. Suppose let's consider the one day energy consumed by these three devices. Okay, so this is one day. In one day, you use this much. Okay, so let's calculate. Let's say calculate how much kWh, okay, kilowatt hour, as for these three devices combined. Okay, and then if each 1 kilowatt hour you pay like 50 cents, how much money does it cost for one day, okay, of these three devices? I guess this is a pretty simple exam exercise, but let's do this one, okay, just for fun. I guess this is a pretty simple problem. So probably most issue just from math. First of all, let's calculate the total amount of energy used in the day, right? So with those things given, so basically I want to use kilowatt hour as our unit. So I'll convert everything here to kilowatt. So it's going to be 0.2 kilowatt times 24 hours plus 0.1 kilowatt times 8 hours. Plus 0.085 kilowatt times 4 hours. Okay, so just these three together, right? When I did this calculator, I got 5.94 kilowatt hour together. Okay, so a lot of you guys get a lot of different answers. Well, we do it quickly here. Each one of these, right? This is going to be like 4.8. This is a 4.8. And this is a 0.8. And this is a 0.434, right? So you add them together, this give you 5.6. This give, then plot this is 5.94. So the total energy consumed per day by these three devices combined is 5.94. Okay. Now if you multiply this by the 15 cents, so this gives you like 5.94 times 0.5. You got 2.97. That's going to be how much you pay, right, for the this is how much you pay for the energy for these three. Yeah, this is per kilowatt hour. So as you see here, right, if you use these three devices this much every day, it's cost you like about $3. Okay, well, this doesn't sound like a big deal, but if you do it for 30 days, it's gonna cost you $90. I guess probably this 50 cents is overestimate. You probably pay less than that for your electricity, but that give you an idea. Whatever you have, next time when you get your electricity bill, you don't have to just tear it up, throw it away. you can take a look of how much energy is there actually, and then what is the rate per kilowatt hour, and then you can have an estimate. You know what? Sometimes they mess up your electricity bill. They would put a number that's way bigger than you actually use. I don't know why, but they give, sometimes they said they do a fair estimate. Instead of looking at your meter, they just estimate it, which is sometimes totally wrong because you may not be at home, you know, you may travel outside or something, you know. Anyway, this is about that one. So we're done with this chapter, okay? Any question about this problem? Good, okay.